Okay, so I'm going to go, and we're in chapter 5. We're silicone control rectifiers. And we're talking about the Battle of the Bulge, 1943, 43 to 44, right? No, 44, 45. Was the first time we had a silicone control rectifier on the battlefield. It was doing the proximity switches for our artillery pieces. And the Germans didn't like us because our artillery shells were blowing up above the ground, filling their foxholes with shrapnel, and they were unpleased. Anyway, the silicone control rectifier has 4 different things: a P and N, a P and an N, an anode, which means positive, a cathode, which means negative, and a gate. So this thing turns on when I'm positive at the anode, negative at the cathode, and the gate goes positive. It also will turn on if I'm negative at the anode, positive on the cathode, and I go negative on the gate. It'll also turn on if I put too much voltage across it. It'll also turn on if some cosmic ray goes and hits it at the wrong time and it's looking funny. That'll happen. It'll also turn on if it overheats. So it could overheat and turn on. So there's 4 different times that it can turn on. But what it allows me to do, it allows me to control in the forward half cycle or the negative half cycle. So it's going to turn on someplace in the first quadrant and stay on, and then turn off it'll commutate, turn off when I pass through 0 and go the other way. So in a 60, it's something you use in a 60 cycle power supply. It's turning off 60 times a second. It's turning on 60 times a second. We can think of it as an NPN and a PNP transistor back to back. We normally don't. We just think of it as an SCR and let it do what it does. It has a voltage that turns it on. When the gate turns on, this guy turns on. So if the anode's positive and the gate goes positive, boom, he turns on. Looks sort of like a transistor, but not really. There is a negative resistance area right there where my curve is negative, but it's a transient thing that happens so quick we can't take advantage of it. So we have forward blocking region where we're off. We have some current where it turns on. Once it's on, it's on. It can go down, it can break off, it can have an avalanche region where it's trying to burn up. It can do that. We normally throw some resistor in going to the gate so that we have some time that we come on. Depending on the temperature will depend on how much voltage I have to have or current I have to have at the gate. So this is temperature, and this is milliamps of current going through the gate. At a high temperature, I need less than 5. At a higher temperature, I'm going to need 20. This is a logarithmic graph if anybody cares. Voltage at the gate, the same thing, is in conjunction with the temperature. So I only need less than 0.5 to turn it on when I'm hot. When I'm at room temperature, what's room temperature in Celsius? 40, right? 40 is room temperature in Celsius. So I'm going to need a little greater than 0.6 to turn it on at room temperature. If I'm in the middle of the Antarctic, I'm going to need a little bit more to turn it on. Holding current. Once it's turned on, it stays on unless not enough current's flowing through it. It stays on until it's commutated. So when it goes negative, it's going to turn off. But I have holding current. That's not a whole heck of a lot. I mean, even at a low temperature, we're only talking about 20, 30 milliamps. At a higher temperature, we're talking about 9 milliamps. So I need 15 milliamps to turn on the LED. So if this guy's turning on an LED, he's going to stay on. If he's turning on something like a 3-phase motor that's 10 horsepower, then milliamps is not the issue, right? Yeah, pretty much. So I've got some triggering circuit that's going to trigger this guy on, and I've got some load circuit. In this configuration, when I trigger on, the load is on. when I trigger off, the load is off, and I'm not sure what those guys are doing over there, but they're doing something. Snubbing circuit. So this guy is preventing an overcurrent situation to the load, I think is what he's... Oh, I went too far. Okay, so now we see our signal. The AC voltage is coming to the machine. My silicone control rectifier is off, and then it turns on. The voltage across the silicone control rectifier does that. I commutate. I'm off. I commutate. I'm on, and I see it, and then both I turn off again. I'm only controlling in the first 90 degrees. You see that? I'm not doing something in the third quadrant. I'm not doing something in the fourth quadrant. I'm not doing anything in the second quadrant. I'm only turning it on and off in the first quadrant. A problem that will be corrected before half past the hour. Okay, well, clearly I can buy silicone control rectifiers. They look sort of like transistors. They have 3 leads. They normally have a great big hunk of heat sink material associated with them that I can attach to a bigger heat sink because these guys are going to get warm. I'm going to have some current restrictions. I'm going to have some voltage restrictions. And now I have configurations where I have them in, turning things on and off. So here he has to be on in order for the load to have power. And there I've got some voltage divider, some switch, and I'm turning him, my voltage, or I'm turning him on. Voltage at the gate going up and down. When the voltage at the gate gets hot enough, I turn on. When I turn on, I have some current going to the load. Okay. Triggering using a resistor and a capacitor. Now the capacitor is charging up and discharging 60 times a second. Okay, so this guy is every time it commutates, I discharge the capacitor, and now I'm going to charge it back up again. I'm trying to control where in the first quadrant this thing is going to turn on. So between 0 and 90 degrees, am I going to turn on at 45 degrees, 90 degrees? I'm not going to be able to turn on in the second or third quadrant, but I'm going to be there. Here we go. We have 2 silicone control rectifiers in a circuit to turn AC into DC. So now I'm going to change the amount of power I'm sending to my load, and I'm sending it as positive half cycle power, and basically I'm changing the amount of power. So I could go in and in that application have the lights in my dining room dim. Okay, and the best I could do is get rid of half the light, because I'm still going to have the other half. Okay, here we are, we're changing the firing angle again. Now we have them wired in so that we're actually doing it in the second quadrant, but we're not, because each of them is really a first quadrant device. I can put them in a bridge. So here's a normal bridge circuit. Now I have a silicone control rectifier controlling power going to the load. I have silicone control rectifiers in the bridge circuit itself, which would be a normal thing to do. Now I can vary the power supply by doing that. This is a Schottky diode. It has an anode, it has a cathode, and it's going to be used to turn on the silicone control rectifier. So I'm going to buy one of these to have them turn on at 2 volts or something. Here is my characteristic curve, and we notice that we have a negative resistance region. And for those that, did I put the negative resistance problem on the final last semester? Do you remember? I'm pretty sure I did. I'm pretty sure you all missed it. On the final last semester in the circuit class, I'm pretty sure you had a problem that had a resistor that was negative. Yeah, I'm pretty sure you did.
You hosed us.
Yeah, and I hosed you over. You all missed it. Yeah, I told you about it earlier, but you all forgot about it. So anyway, so here's a device with a negative resistant region that we can in fact use if we wanted to. There's not very much of it, but we could use it. Okay, well now we're going to do something, and we're going to go to a diac. So a diac is something that's going to control first and third quadrant, and it will turn on in both directions. So in an AC circuit, it's going to turn on going both ways. And we're going to use it as a control device. We're going to think of it as a Zener diode that can turn on going forward or backwards. So it's going to turn on at 2 volts or 3 volts or 4 volts, whatever. And so now I have a turn on region going in both directions. Okay, so there is my unijunction circuit. So this is a unijunction transistor, and a unijunction transistor is one that is programmed to come on at a particular voltage again, and I can buy it for various voltages. Another interesting symbol. So I can throw all kinds of symbols on the next test, ask you what they are, and not worry about everybody getting an A, right? And the unijunction transistor does something weird. And so that's what it is. It's a characteristic curve. It goes into saturation, it goes into cutoff, and between saturation and cutoff it has a negative resistant region. Isn't that lovely? So here in your labs, there's a lab that does unijunction transistors, and I have that equipment if you want to do it. When you put it in your oscilloscope, it's telling you have this peak here that you're going to see. Well, I'm telling you right now, you're going to have to turn the lights off in the lab to see it. It happens so quickly, it's so faint that you're not going to see it unless you turn all the lights off. So if the normal lighting is on and you're doing the lab, you're going to come get me. You can't see a damn thing, which is normal. You don't have my trifocals. And then you would go in and what? And then you'd go and I'd turn the lights off. Everybody else, everybody else is like, what's going on? And we just ignore the rest of it. Steve's crying about he can't see, right? And we'd take 15, 20 minutes to show you that your oscilloscope's working just fine, and then turn the light back on. By that time, Steve would be asleep and wouldn't be a problem. But when there is now if you do it in multi-sim, it's not an issue. The oscilloscope's going to show you the trace. You don't have to turn off the lights. So this is the equivalent circuit of a unijunction transistor. That looks like a diode with a bunch of resistors in it, so must not be very much. This is a put, which is a programmable unijunction transistor. So this guy can be programmed by his gate to come on or off at a particular time, and so that's pretty cool. So now my negative resistance region can be made bigger because I have the capability of changing that one. Now, back to what I said about the operational amplifier. We're going to take a month in the devices class. Well, the same thing with all these other parts too. We get to look at them again in the devices class a little more closely. So here's a relaxation oscillator. So I got some input. Well, I have some power to it, and it's giving me a sine wave. Is what it's doing. And I can change if I change the capacitance and the resistance, I can have a different frequency on my sine wave. So here is a unijunction transistor being used to turn on the SCR. And There it looks like I just have just a regular PNP transistor turning on the SCR.
How can you tell the difference between the NPN and the PNP?
Oh, that's easy. This is obviously a unit junction transistor because that's where we are. The PNP would go up like that and down like that, not straight across. Okay, this is called a Crowbar circuit, and what it's for is to prevent your prevent power surges. So I want to have 5 volts on the output, and I don't want to draw 50 amps and blow something up. So I would have a circuit that looks like that. If I go over, I get to 6 volts, I say, oh, that's too much, and I use the SCR to throw away the extra. And why we call that a Crowbar circuit, I have no idea. That's lost in antiquity too. So here we're using a Zener diode to turn on the SCR. Again, preventing an over voltage situation in my power line. I would not do this with DC power. I would do this with AC power. And if I'm doing it with AC power, then this is a very big SCR that can allow lots of current going through it, right? Now I have an operational amplifier doing line regulation. So I'm sensing the power line and deciding whether or not the voltage is the right voltage and doing something with it. Now what is this guy over here? Anybody know what that symbol is? Yeah, I have no idea either, but I'm sure we're going to cover it later. Okay, now, this is the cool thing. This is a triad. So now I've got 1, 2, 3, 4, 5, 6, 7 layers of doping going on. I don't have an anode and a cathode. I have a main terminal 1 and a main terminal 2, and I have a gate. This guy can control in all 4 quadrants. So unlike the SCR, where I'm stuck with turning it on and off only in the first quadrant, this guy can be turned off in first, second, or third, or fourth quadrant, on or off. He still is going to commutate, so when I pass through 0, he's going to turn off. But on turning on, I can pick the quadrant and he'll turn on in that quadrant. I go both ways, just like the diac did. So now when I turn on, and what it's saying is that in quadrant 1 with main terminal 2 positive and the gate positive, I'm going to turn on. In quadrant 3 with main terminal 2 negative and the gate positive, I'm going to turn on. In the other quadrants, I'm going to be positive on the main terminal 2, and I'm going to be negative on the gate. I'm going to be negative on main terminal 2, and I'm going to be negative on the gate. And you're not going to remember that, but that's okay. What's important is that you remember that this guy turns on, can be made to turn on in all 4 quadrants. When I buy a light dimmer for my house, this is what I'm buying. So when I'm using a Triad dimmer circuit in the dining room. So that's what I'm doing. So here we're showing that I can turn on in multiple quadrants, depending on who is positive and who is negative. And now we have a way to do it. So now I'm gonna turn on the Triad, and I have a variable transistor and a resistor, so I can pick a voltage and turn it on. It looks just like the SCR. Is only going to have 3 terminals. It's going to have a great big huge heat sink. Sometimes the heat sink is one of the terminals, and so it'd have two wires coming out and a great big heat sink. That great big heat sink is the other terminal, so it could be main terminal 1, for example. I can buy these guys to pass thousands of amps at thousands of volts, or I can buy them to pass precious little at precious little. So these guys come in all forms. And I'd memorize this particular chart if I were you. This looks very important here. So so it's square, right?
Picture time.
Yeah. All right, so we can think of the triac as two SERs with two separate gates. So we could think of the triac that way, although the triac only has one gate. But if we put two SERs opposing each other with two different gates, we would have the same effect as having a triac. So now I'm triggering my my triac with a unit junction transistor. So to answer the question that Raimundo had,
Yes.
this is a PNP transistor because my arrow is pointing in. Okay, so that makes that a PNP transistor. This is a unijunction transistor because I am square on the wires coming in and I'm at an angle with the pointer there.
Unit junction?
Yeah, unijunction transistor. And
The other one is PNP.
the other guy's a PNP. Yeah.
So how do you tell it's NPN then?
Well, an NPN is going to have this arrow thingy pointing out, pointing in the opposite direction of that guy.
Oh, okay.
Yeah.
So the one by the resistor 4 would be considered what? On by resistor 4?
The capacitor by resistor 4?
No, on that the arrow.
This is a PNP transistor.
I know, but see if you get the resistor right on
It's
R4.
up on potentiometer.
This is a resistor. Yeah, what about it?
The one on the bottom.
This is a resistor. This is a potentiometer. Yeah. Yeah, we actually use those in the lab. I know. It's Steve's trying to make one work now. He's on lab 16 and he's been there for 4 days now. And step 1 of lab 16 says make a design and have the instructor approve it. And, so far there's been there's only 2 parts required, but so far I don't have any design. Yeah, write that down. 2 parts.
Yeah.
See if that helps any. Anyway, so this is I'm triggering the triac. Normally I like to trigger my triac in a natural way. So this would be a more natural way to turn it on. I have some AC voltage coming in, and my capacitors are charging and discharging, and my triac is turning on. And when it turns on, my load gets power. So when the triac's on, current flows. When the triac's off, no current's flowing. And I've got simple AC switches, so I'm just going to take a switch and turn on my triac with the switch. Now, if I take the switch and turn it on, then the triac turns off and on every 60 times a second, because this guy's going to commutate every time it passes through 0, and then it's going to turn on again. So, and in fact, it's going to turn on in 2 different quadrants. So either first and third, or second and fourth, depending on what my voltage is there. So that's how that's going to work. Now here, I'm using voltage coming in, but it's a sinusoidal voltage that's building up. But he's still going to turn on in 2 of the 4 quadrants. He's going to turn off when it commutates, when the sine wave goes through 0, he's going to turn off, but then he's going to turn on again in the next quadrant. So Steve is looking at me like I don't have a clue what I'm talking about, which is probably the case. I mean, that's the big picture of things, but that's what I did last time. Okay, so I look at this guy. And my voltage in is doing this, up and down. Okay, and my voltage is positive there. Therefore, if I'm positive there, I'm going to have a first quadrant turn on. So I turn on in the first quadrant, and I turn on in the third quadrant so with positive at the gate, and I'm positive to negative, I have a first quadrant turn on. When I'm positive at the gate and I'm negative positive, I have a third quadrant turn on. Okay, so I'm going to turn on in both the first and the third quadrant. My gate voltage is always going to be a positive voltage because I got a battery there. Now, in this case over here, I turn on the switch. Positive on the gate, on the positive half cycle. I'm positive, I'm negative on that guy, so I'm going to be a first quadrant turn on. This guy, when he stays on until he commutates, so he commutates when he passes through 0. Now my switch is negative, and with this guy negative and that guy positive in the third quadrant, I'm going to turn on, so I'm going to have a third quadrant turn on again. So this guy's going to give me a no. He's going to give me a fourth quadrant turn on because I'm negative on the gate and I'm negative positive on those guys. All right, well, I'm sticking with it, whatever it is. And all right, now we have a gate-controlled switch. So, funny-looking thing. If I do a transistor model, I have an arrow going in, arrow going out. Notice that I'm not using words like emitter, collector, base anymore. I'm using cathode, anode, gate. Emitter, base, collector are words we use in a device that we have some biasing associated with it that's DC. Anode, cathode, gate are words that we use in AC devices. So I wouldn't use the word anode, cathode if I was talking about DC normally. Just one of those things. I think it has to do with the French. The French used to be on my list as bad people for a long time. They're on my list with the good guys now. They just kicked ass at Molly, so they're
about time to do
yeah, about time. But so I can't make those French jokes that I used to make,
I'm sure they're still fun.
Yeah. So here's a silicone, a gate-controlled switch. So I'm gonna turn on and turn off, and when that happens, I'm gonna go and make spikes. I can't think of any good applications for it. It exists. We don't make them in the lab. Probably it's used in our power flexes to control power spikes, and that's why we have, even though we've tried very hard to wreck those things, we haven't been able to wreck them yet. That's probably why.
Not yet, Steve.
Here's that we know about. Here's a silicone control switch, and this guy's got a cathode gate and an anode gate. So, and again, he's in charge of turning on and off, switching things. So we could go and call up Fox News and tell them, what do you mean you don't know why the power went off during the Super Bowl? It's obvious. Some silicone controlled switch failed. What's wrong with you guys? And they'd scratch their heads and who is this guy anyway? He's calling from Iowa? What does he know? What does he know?
712.
Yeah. Calling from Iowa. So here we have a silicone controlled switch in some circuit. It's turning on, giving power to the load. It's turning off, taking the power away from the load. So silicone bilateral switch. All right, so yeah, that does it. I mean, what happened in the 50s is that you had all these guys in their garage making up silicone devices and just dumping P's on top of N's and hooking wires willy-nilly. And so for every 100,000 parts they made, there was a part that was actually could be used for something, and it got a name, and then we have to study it. So this guy here turns on in both directions and isn't that nice. but he's got anode 1, anode 2, and a gate. Silicone bilateral switch. So he turns on in the positive half cycle and the negative half cycle both. And there's the schematic of that switch. I know that we're going to have that guy memorized too. And, anyway, I don't even know what that stands for. But, oh, we threw a Zener in, so now it's cutting down the forward breakdown voltage. So that's good, isn't that nice? So now, how are we going to test an SCR? So we think it's busted. So we're going to go and put an ohm meter on it. So here we go. We got a problem with the circuit. I wonder what the problem with the circuit is. Oh, this is the circuit for problem 1. Oh, that probably means I'm done, and I can do the homework now for what chapter are we in? 5. And it's not even 11 o'clock yet. If I get done with the chapter 5 homework, then I go right to chapter 6. We'd be back on schedule. That would be awesome. How do I get out of this transparency thingy anyway? All right, there we go. Now we're all set. So we're supposed to do homework problem 1, 2, and 18. And I already found the schematic for problem number 1. Isn't that good? Now all I have to do is get the schematic for problem 18, for problem number 1, into my smart board. All right, excellent. All right, I'm on page 262, and calculate the values of R1 and R2 in the circuit of figure 552 and describe the type of circuit this represents. Calculate the values of R1 and R2. Okay, well, what do we know? Not much, right? But we know that we're at 60 hertz. So we'll start there. We're at 60 hertz. And we know this is an SCR, so we know we want to control it in the first quadrant. So those are the two things we know. And we know this thing's going to turn on at somewhere around 0.5 volts. We know that too. All right, so now we want the what do we want the time constant to be of the circuit going this way? Let's say 60 hertz implies 17 milliseconds. Okay. And so if we had the resistance set too high, let's say we wanted to turn it on there. We want to know. We're going to divide that by 4. What's 6? That's 4. So 4 milliseconds basically. Okay, so if I had a time constant that kept this from getting to 0.5 volts in 4 microseconds, then I would never turn on. Okay, so that's the issue. So that would be my minimum resistor for this guy. Or would that be my maximum resistor? That'd be my maximum resistance that I could have. Okay, so that being the case, we want 120, 1 minus e to the minus tau T to be 0.5 volts when T is 4 milliseconds. Is that what we want? Anybody have their circuit analysis book with them? You do? See if that's the equation.
Let's go.
Anybody got a good page to look on? Capacitive RC circuits. I think it's going to have to be in 13 time. Control, what do we do? Control Shift. Okay, we're going to use an equation on page 528 of your circuit analysis book, and it says T is going to be minus tau natural log of 1 minus the voltage on the capacitor divided by the voltage on the source.
So little t.
Yeah, so time is that. So that's the, thank you, Raimundo, for allowing me to.
What is that, ln?
Natural log. Okay, so we know our time is going to be 4 milliseconds. We don't know our tau, so we're going to keep that. Natural log 1 minus the voltage across the capacitor is going to be 0.5 volts. The voltage of the source is going to be 120 volts. Okay, so tau is going to be minus 4 milliseconds divided by natural log 1 minus 0.5 divided by 120. And maybe my calculator has enough light. Maybe it doesn't. Who knows? Okay, so I got 1 minus 0.5 divided by 120. Okay, that's the number I've got. Okay, so I've got natural log. Who hid the natural log key?
Texas instrument.
Yep. Set up right underneath second.
Yes,
Button.
I see it. Okay, so natural log 1 minus the answer. Okay, 1 over key. Second function 1 over key times 0.004. Okay, so I'm going to get that tau, my time constant, is going to be minus well, it's going to be positive 0.0007298, and tau is RC. Okay, so R is going to be 0.0007298 divided by the capacitance, which is 0.47 microfarads. Okay, so I've got that guy divided by 0.47 double E minus 6. Okay, so I've got 1.5K. So that's the worst case scenario would be it doesn't turn on until just before the 90-degree part, and I'm going to have 1.9K. So that being the case, I'm going to put
1.9 or 1.5?
1.5K. I'm going to put a 500 ohm guy there and a 1K guy here and say that that's perfectly okay. I could do another calculation to see how early it would turn on in that case. And if I needed more, if I needed to get rid of more of the resistance, I could, but that would probably be an okay thing to do. Okay, wasn't that interesting? Anybody believe that answer at all? How many think I just pulled it out my ass?
Don't.
Of course, do that all the time. What's wrong with you guys? Yeah. Natural log. Oh, want to come down a little bit? But you'd have to, you know, why in the industrial book would the author, you know, have you use a natural log for? So there's obviously a more common sense way to do it, but obviously that worked just fine. So
Natural log times 1.
Huh?
You scroll down one, please.
Or are you not getting the same answer I am? Oh, probably parentheses. Yeah, if I would have gotten some fractional ohm, I would have known it was wrong. If I gotten mega ohms, I would have known it was wrong.
That's 4,000.
That's 4 mils.
Oh, it is 4.
0.004.
Yeah, it is 4.
0.004. Yeah.
Can you get some?
Okay, well, we're going to proceed to the next problem,
Let's just keep going.
which is number 2. I have 6 minutes to get the next 2 done. Do I have a diagram for the next guy?
What number is the next one?
Yeah, that's for that guy.
Oh, is that on? Okay.
Next guy is problem 4. Nope, I don't have a diagram for problem 2. Okay, so problem 2 says, draw the voltage waveform across an SCR and across the load of a firing angle of 65 degrees for the circuit 552. Well, that's the one we just had. 552 is the one we just had. And an AC input of 1 kilohertz. Now, why would we? Who has a 1 kilohertz AC signal coming into their house? You know what is this anyway? So I got 1 kilohertz.
It's 1 kilo ohm.
Where? I don't see kilo ohms anywhere. Anybody else see kilo ohms anywhere on the board? Here, borrow my glasses. What do you see now?
Hertz. There you go.
All right. So here's my. So I'm going to draw the waveform. All right. So that's my voltage in. When the SCR fires, I have voltage to the load. All right, so this is going to be my current to the load picture here. That's what what am I supposed to do? Voltage waveform across the SCR and across the load. Okay, voltage across the load. Voltage load. Okay. And I have a firing angle of 60 degrees, so I'm going to draw a line down at 60 degrees. That's clear to everybody, that's 60 degrees, right? And that's my firing angle. Okay, so before the SCR fires, the voltage across the load. Now we need voltage across the SCR too. All right, one more picture. Voltage across the SCR. All right, so the am I stalling? Is that what's happening here? Oh, there I did it. Did it again. Okay, so now the voltage across the SCR comes up when I fire it go, why am I in this color? So I come up, when I fire, I do that. When I cross 0 and I commutate, I'm going to cross 0 and I commutate, the SAR is going to go and follow that waveform down. Follow it back up until I fire. Then it's going to follow the waveform back down until I fire. Okay, so that's the voltage across the SCR. So now what is the voltage across the load? Okay, so the voltage across the load is going to be, if there's no current across the load, what is the voltage across the load? So the voltage across the load is going to be nothing, and then it's going to come up and follow the waveform until I commutate. And then it's going to stay down, and then it's going to stay down, and then it's going to follow the waveform until I commutate. Well, except for the really shitty picture, that's what it's doing. I think, oh yeah, that's pretty bad. Okay, that's bad. Okay, get rid of it. There we go.
It passed.
All right. So
Boobs.
we'll go and do it this way. Boom, boom. Follow the waveform. Boom.
That's a good move. Banana. What kind of boots you got?
Follow the waveform. Okay, is that better? Okay, so that was number 2. Number 18, does it go that high?
No?
Yeah, it does. Wow. Number 18. So now we'll go back and see if I have a diagram for problem 18. And then I don't have to draw one. When you know it. I have one for 17. Problem 18. What value of R1 will cause the diac to break over and the triac to conduct? Well, that's an interesting question, considering it doesn't tell me what figure I'm using or anything else, right? We're probably talking about figure 17. Okay, so we're talking about this guy. That's fine. So we can all agree that this is also for problem number 18. Right, so this is problem 18. What value of R1? Okay, so we got to get a value of R1. Right, so that's what we're doing. And this diac, it doesn't say. The diac in figure 556 has a firing voltage of 30 volts. Okay, so this guy needs 30 volts to turn on. And we want to find the value of R1 that would cause this to happen. All right, so the first thing we're going to look at is the time constant, RC. And the time constant is 390 times 0.47 microfarads. Okay, so 390, 390 times 0.47 E minus 6. And it looks like I've got 183 microseconds. Okay, and we know, because we're at 60 hertz, this thing is happening in 17 milliseconds. So in 17 milliseconds, my wave's going up, down, and back. So that's my period. 17 milliseconds. Okay, so we want this to get up, we want that point to get to 30 so that I turn on. Okay, at a firing angle of what does it say? No, it doesn't say what the firing angle is. Okay, so we just have to get there. All right, well, if we ask ourselves 5 time constants, I'd be fully charged, right? So 5 time constants. All right, 5 time constant. R1 plus R2 times C. Okay, so 5 times my answer. All right, so I want 0.9 to be R1 plus R2 times 0.47 microfarads.
Where'd you get 0.9?
I multiplied that times 5
Okay.
because that's, so I took that guy and I put him there. Well, I didn't put him where the 5 is, I put him where the T is. All right, so R1 plus R2 has to be 0.9 divided by 0.47 microfarads. $1,590 ohms. Now I already have 390 sitting there, right? All right, now, but I don't need to be fully charged. I only need to get to 30. Okay. So I look at this and I say, I'm going to get to there, and I'm going to get there in about 4 milliseconds, but I want to get to 30 volts before I get to 120. That's my plan. So I'm going to do it because my time constant 5 times tau is so big. I'm going to be okay. Probably. If I have that, then I need this. Okay, so I should be all right. What was the question? R1. If I have 390 on R2 and I subtract that, 1950 minus 390, 1,560 ohms. Okay, now ask ourselves the question: what question is being asked? Is the question being asked, what value should R1 be set to? Or is the question being asked, what value should R1 be? See the difference between those two questions?
What value of R1?
What value of R1?
Break.
Okay.
Which one would you buy? So we're gonna break it.
So I think that any value of R1, I think that R1 should be 1.5K, and any value less than 1.5K will cause it to break over in the time allotted. That's how I would answer the question. Now, do we have a 1.5K ohm potentiometer that's cheap because they mass produce it? The answer is no. So that means that a better answer would be R1 should be a 5K potentiometer, and that values of R1 from 1 to 1.5K would cause what we're looking for. That's how I would deal with that particular problem. Okay, let's do a pause here for a moment.